Any questions so far? No? Okay, so moving on then. I'm going to show you on PysDate how to enable memory debugging. I will show you two things for sure, which is first of all how to find dangling pointers. Second, I would like to show you how to detect memory leaks, typically leaks that could lead to a memory exhaustion. And if we have time, and I think there will be, I will be able also to show you the guard pages in action and how they would help during your bug resolution. Right, so first of all, I'm using Allinea DDT. So this is what we have seen in the previous webinars. I've started the Allinea Forge client and I have connected to the CS system. If you want to see how this works, I encourage you to look on YouTube. Jean-Guillaume has posted a few videos, tutorial videos for this on PysDate. So just follow the instructions and you'll be fine. Once the remote client is connected, what we want to do is have a look at our code. So in this code, this is a very small example. It's called cstartmpi.c. And in this application, I have first made sure that I have compiled the application with the -g-00 options. I also have added this line of code and this line in the linking flags, which is important. This ensures, so if I make this a little bigger, this ensures that we are linking the debugging malloc library towards the application. So if I compile my code with this, everything looks fine. If I execute my application, it should run perfectly fine as well, but I know that there is a bug in this code. So what I'm going to do is I'm going to run this code with Allinea DDT. So I'm typically adding the DDT -- connect in front of the AP run command that I would use every day. So if I do this, so sbatch of my job, so the job is submitted to the queue, and when the job starts, I get a reverse connect request telling me I would like to debug my code, so I accept. Now it will take a few seconds because I'm working remotely and the date system is 2 hops away from me, but I will have in a few seconds the run dialog where I can change the memory debugging options. Okay, just waiting a few seconds for this to happen. There we go. So here is my run dialog, which is the screenshot I have showed you before. To enable the memory debugging, I just have to tick this little box. And for this particular example, this is the only thing I need to do. In any case, I cannot use the preload memory debugging option. I have manually linked the application towards the dmalloc library. And here is the menu where you can choose between fast, balanced, and thorough memory debugging. So you see that the more I go towards the left, like for instance, the thorough memory debugging up, you see that you have the series of keywords that are enabled. And for instance, the free blank option that I mentioned earlier is available here. If you go to a custom level of memory debugging, you can choose what you want. And you can say, all right, I just want to use my free blank option throughout my code. And it's perfectly fine. So in this particular example, I would just stick to a basic memory debugging. The second option we discussed were the guard pages, and these are the guard pages. This is where you can create them. So you can choose how many guard pages you want to enable. Typically, a guard page is 4 kilobytes. It can be more depending on your operating system and how the kernel is configured. But typically, you would keep 1 or 2 guard pages, and you can choose here if you want the guard pages to be done before or after. We discussed about the overhead. These are the options that you can change to tweak and control a bit the overhead of the memory debugging. But in this particular case, by default, it's perfectly fine. It will run nice and quick, no problem. So when you're satisfied with all this, you click on OK, and you run your application. When you're using the debugger, it doesn't make any difference what you're doing. It doesn't make any difference whether you're using memory debugging or not in terms of usability. It's always DDT as usual. Everything is the same. So there will be nothing new for you here. It's all standard. So my job is starting. Processes are connecting to my graphical interface. And once this is done, I will be able to see the variables, my source code, and everything I need to debug my application. Okay, I'm taking a few seconds here. All right. So here is my code. So what I want to do is I will want to start my application in order to debug it. I'm going to show you just how to change memory debugging options at runtime. So this is done in the control menu. So if you go to control, once this is done, you can see memory debugging options at the bottom. So anytime when your processes are stopped, you can change these options by going into this menu. So there's no secret. This menu is exactly the same one you had in the run dialog. So it's really identical. You see here, this is what I can say. Let's say that for now I want to add, to remove the guard pages. You can just click here if you want to add them. I say, okay, now I want to debug thoroughly my code. You can change this anytime you want. So in this particular example, so I'm running my code. I know there is a problem, but how would it happen? So this is what would happen when you have a memory bug in Allinea DDT. You execute your program, and at some point there is a failure, and Allinea DDT will tell you, you have a memory error on line 98. So it tells you the memory debugging library has found the bug, and it will also tell you what kind of problem you have. And in this particular case, it is telling, Allinea DDT is telling me that I'm trying to read or write an area or a zone of the memory that has been previously freed. So I want to pause my program, and I would like to investigate what is going on. So what's going on is that we are accessing this particular array. So we can investigate, right? Let's have a look at the pointer details. So if you go to the menu here, if you do a right click, you have view pointer details for this particular array. So this is the array we want to investigate. So what has happened? And what we see is that in one click, I retrieve two different things. The first one is telling me that this array was allocated on line 93, which is here in my application. And on the right-hand side, DDT is telling me, well, this array was deallocated on line 95, which is here. So basically what has happened is, this is a stupid error, but I have created an array, I've released the pointer, and I'm still using the pointer on line 98. So here with the memory debugging, in one single iteration, I have found all the information I need to fix this bug, right? So this is a very simple bug, but this is typically a bug that is called dangling pointers. And you can see that with memory debugging, immediately we know where the problem is and how to resolve it. So how to resolve it? Very simple. We remove this free from this particular line, and we put it somewhere towards the end of the program, for instance here, when we are sure that we do not need this array anymore. Okay, so if I save my program, you can do this with Control S. You have edited the code, saved it. You can recompile the code using the build command, right? So here we go, my code is recompiled. If I restart my job, I would be using the new binary, and there would be no more crash in my application. So this is one first example of memory debugging. This is a dangling pointer, typically a memory leak that can happen, and it's quite common with complex HPC applications. If you have any question about this particular example, don't hesitate to ask. And as the questions come in, I'm going to start the next demonstrations